Okay, hello dear Meatbags. Let's start our course lesson. And today we will talk about what we didn't uh, do yesterday, and then continue to applications of hyperbolic geometry. So let's have a quick recap of what we already know. So I introduced inversion and stereographic projection. Inversion is space transformation which is defined like this on the picture here, and it is basically for us for at least three models of hyperbolic space is like a mirror symmetry with respect to the hyperplane. Yeah, since I just forgot to tell you yesterday about this, and this is somewhat important notion probably for work, at least sometimes. So that's how it is. And yeah, so inversion changes orientation for our geometric body. So and we take and we constructed the whole group of hyperbolic motions for plane, for three-dimensional space, for n-dimensional space. And yeah, so actually for the plane there were group formed of, I lost it, here, of fractional linear transformations with A, B, C, D real numbers like this, and this is for upper half plane model, and determinant should be positive for the model of Poincaré, ball model. We just take other set of coefficients A, B, C, and D. They just belong to different set. So stereographic projection is such a projection, central projection from sphere to hyperplane. Inversion is a stereographic projection. And okay, formulas of motion. That's what I already. That's what I already told you about. So I will. So some relations with quaternions. Okay. So I introduced hyperbolic trigonometric functions, hyperbolic sine, hyperbolic cosine, hyperbolic tangents, and several others. So we know that actually hyperbolic trigonometric functions are functions of the so-called hyperbolic angles, which is not an angle at all, but it is somewhat like an area of a curvilinear triangle. Yeah, like this. Okay. And they will be important for some formulas, even in applications. Okay. And this is the part where we stopped. So I introduced metric tensors. I even tried to compute one metric tensor, but I made a mistake last time. So I will correct my mistake in final lesson. And yeah, so this is a way for computing lengths in this model, also maybe for areas. So actually there is an elementary formula for lengths in several models with the usage of cross ratio. Okay. And now let's continue to section of curvature. This continuation of differential geometric way for computing everything actually will be an important notion. And also I have to say that I don't have much time for introducing it very thoroughly, so I will just show you an idea and or remind you if you just took your differential geometry classes far away from this moment. So let's watch the video. Actually, okay. Oi.
We see that at any point in n-dimensional space, there are n independent directions, and each line through a point can have a different curvature. Here we picture just two. In one direction, we have a positive curvature. In another, it is negative. We can also construct a surface for each dimension. Each surface has a size and an orientation. We can use vectors to mathematically represent the size and orientation of the surfaces. And for each surface, we can construct a vector that represents the curvature of the lines through a point on the surface. Multiplying these two vectors creates a mathematical object called a tensor. The power of tensors lies in two basic characteristics. First, they carry a great deal of information. And second, they are invariant when the coordinate systems are changed. In other words, they remain constant across all kinds of changes in how we're looking at any particular situation. Riemann developed the mathematics for this generalized space with any number of dimensions. Basically, he came up with a three-step process. First, we define a metric for the space that allows us to measure distances. Second, we use the distance metric to find the geodesics for the space. And third, we use the geodesics to define what we mean by curvature. These spaces are smooth. By that I mean there are no abrupt changes. Given that, we can always zoom into a curved space to the point that the small piece we are looking at is flat. And in flat space, distance between any 2 points is defined by the Pythagorean theorem. We then generalize by adding coefficients to take into consideration different scales or lines in different directions, and the fact that the lines no longer cross to form right angles. This is called a metric tensor. And finally, we extend the number of dimensions and generalize the coefficients to be functions of a location to take into account curved and changing coordinate systems. This generalized metric tensor is the foundation for non-Euclidean geometry, its geodesics, and its curvature at any point. With the metric tensor, we can measure distances between any 2 points by adding up all all the small distances along the way. Taking the formula and finding its minimum is an exercise in calculus that gives us the shortest distance. These are the geodesic lines. Now that we have a way to measure distance and find geodesics, we can determine the space's curvature. Riemann used a concept called parallel vector transport. Picture moving a vector around a triangle in flat space in such a way that it remains parallel to the starting vector. By the time we get back to the start, we have the exact same vector as we started with. Now repeat the same exercise on a curved surface, like the surface of the Earth. Start at the equator and point the vector in front of you, facing north. Move north along the geodesic longitudinal line. When you reach the North Pole, turn 90 degrees to the right. To keep the vector pointing in the same direction, it is now pointing to your left, 90 degrees. Move south along the geodesic longitudinal line to the equator and turn right, 90 degrees again. The vector must now be made to point to your rear in order to keep it parallel to the original direction. Now walk west along the equatorial geodesic until you reach your starting point. Clearly, the vector is no longer the same as when you start. The difference is the measure of the curvature of the space you traveled. Riemann developed a tensor that precisely measures how much the components of the vector change when it is parallel transported along a small closed curve. This is called the Riemannian curvature tensor. A subset of this tensor was developed by a mathematician named Gregorio Ricci-Curbastro, where Riemann gives us the curvature for every geodesic. Ricci gives us the average for a volume. With this, we can calculate the amount by which a volume deviates from what it would be in Euclidean space. For example, in Euclidean flat space, the cuboid's volume is A times B times C. The yellow lines represent geodesics inside the box. The volume is less than this if the Ricci curvature in the interior region is positive. In other words, it's smaller on the inside. The volume is more than this if the Ricci curvature of the interior region is negative. In other words, it's larger on the inside.
Okay, so this was about section of curvature. Actually, maybe let's okay. This was a geometric idea behind. Actually, so you see, you saw several differential equations defining this thing, and actually, so yeah, this is formally defined. Actually, I don't want to go deep in this topic, but since actually you for deeper understanding of this topic, you should take differential geometry classes. And okay, so formally you can compute curvature of your coordinates with the so-called Christoffel symbols, which are defined like this. These Christoffel symbols are just coefficients for differentiations of one vector field across the another. So that's the idea behind them. And yeah, so. And then you actually then this defines some sort of differentiation of one vector field across another, and then actually sectional curvature is computed for two directions for tangent vectors with formulas like this. Okay, so this is very computational topic actually. So actually, I highly recommend you to just take differential geometry classes and learn to compute this by yourself. Okay, so there are three types of manifolds of constant sectional curvature. Actually, this thing can be constant for each point in each direction. So each pair of directions, sorry, since I defined it for pair of directions. And so there are just hyperboloid, hyperplane, and sphere. And they are having negative, zero, and positive constant sectional curvature respectively. And this is somewhat, well, we solved it, we actually already solved it somehow. Triangle area is very small in hyperbolic geometry, so its curvature is negative, and yeah, this also appears in models. Okay, so for this sectional curvature, which we denote as -1 over k square for some non-negative number k, we just take triangle in this model and with angles alpha, beta, and gamma, and sides A, B, and C, like you see here. And then we have actually two hyperbolic laws of cosines, which are dual to each other. They can be, one can be derived directly, and the other can be derived from taking some dual triangle. I'm not going to talk about what is dual triangle, just learn what is what projective geometry is for this, since actually we did a lot of projective geometry in this course, but I didn't tell you much about this. Well, this is some these are some relations with different with other areas of mathematics. So yeah, for better understanding, you should learn them, but this is shortly. Okay. Also, we have hyperbolic law of sines for curvature for k equals 1. Yeah, and so you have to usually you have to divide your sides of triangles, your lengths, by k, and then you just get your law of sines. And what is it for? Actually, all the models are for hyperbolic geometry are different just by multiplication of all lengths by k. So they are all similar to each other. Okay. Also, there are several other trigonometric laws, and law of sines is self-dual, since we can take inverted law of sines, and this just say the same thing. And yeah, so actually for large k, so we have actually, this is a hyperbolic Pythagoras theorem analog for hyperbolic triangle with sides relative to right angle A and B and hypotenusis C. We have this law, which actually is a particular case of hyperbolic law of cosines. Actually, there are lots of hyperbolic trigonometric laws, I already said to you, but those are maybe most useful for computations, so I just present them to you. So for large case, we have approximately the following equality, which actually says to us that c squared minus a squared minus b squared is nearly zero. And this tells us that we can do some, so we can think of hyperbolic geometry for a large curvature, or for a small curvature, we can think about it as very similar to Euclidean geometry, but it is just very locally. When you go far away, then this will break. Yeah. Okay. So I promised area formulas. So for lengths of circle, we have something like this nearly exponential formula. And again, it's up to a multiplicative parameter here, and hyperbolic area of a circle is just like this. So it's again nearly exponential. Okay, now let's continue to applications. Okay. So there are some ideas when to apply hyperbolic geometry. Actually, we simply don't know what is the true reality behind all what is happening before us, yeah, and somehow we need. So sometimes there is a hyperbolic geometry behind this, and so. Sometimes your Euclidean intuition doesn't work, and you just use fractal geometry or hyperbolic geometry when your information amount is expanding exponentially, when you need enough of space, when you are not limited by compact ground, when there are lots of exponents, and you need some degree of freedom in your model. Okay. Those are just some heuristic ideas. So maybe for the start we learn something about information theory, and actually, so here you see hyperbolic embedding of quintary tree. Yeah, quintary. So 1, 2, 3, 4, 5 branching. Here is 1, 2, 3, 4, 5. So actually, so all the angles here are equal. Probably you already know what is the angle here. Tell me. Actually, probably some. Yeah, 60 degrees. Since you just divide this 360 degrees by 6 equal angles. Okay. So let's see how to generate such a thing. So firstly, so the main idea here is to generate a solution, and then just take some. Okay, I will explain to you what to do when we know how to generate a solution.
We decide the last plane object with a strict hyperbolic display, equipped with a model.
Sorry. Not sure whether he is speaking English and subtitles are in German.
In this case, length are increased pushing the real path, so it appears like an infinite horizon. Lines, or geodesics, are defined as a short stack of intervals, like straight line in classical geometry. The geodesic with the points on the same axis is a segment of the classical.
So probably let me repeat what he's saying. So he is just simply saying that here straight line is just vertical for upper half plane model.
It's fine. Of two models of axis. However, when they don't have the same axis, the short path.
And here there will be not just a straight segment line, but an arc of circle.
This is the arc of a semicircle meeting our three points, still often belongs to our axis. Our space comes with the approximation PSFG of R, which acts by conformal orientation relation as reduced. This action is transitive of us and transitive.
Okay, so this is about this transformation group. Actually, why here he used such a matrix notation, since actually when you take compositions of such functions, then you just in the result you have just another fractional linear function, and if you just take this matrix A, B, C, D from this matrix, yeah. So if you take a composition of two such functions for two different sets of A, B, C, and D, and then their matrices will multiply. So that's some useful relation, and it is often used.
This action is transitive over once and transitive over derivatives.
So he just did what? He just reflected this half plane into another half plane by the transformation he will eventually write here.
This action is transitive over once and transitive over derivatives. The discrete subgroup of this result is called a it can be group.
Okay, so if you just so function group is just somewhat like a set of motions which is closed under the operation of composition and taking inversion, not inversion but inverse element. Yeah. And so you just doing this, and usually you are taking some discrete subset of motions, and then there is actually a beautiful theorem about this such subgroups, and the history behind function groups is actually very funny, since actually their author is Henri Poincaré, and he called these groups as function, but mathematician Fox, but just to joke about his colleague from Germany, mathematician Fuchs, I don't remember his name, and Fox just didn't have any works about these groups at all.
with this function if and only if points each point control is active and discrete. Here, it's going to go with the point
So this what we get by applying some discrete function group for the 1 point. So we are moving 1 point.
Action of equal to the first function. To describe the action of triangle, we use fundamental regions. The region of the outline is called fundamental of the group.
So he is now reflecting this. Let me call it triangle. Actually, this domain here is nearly triangle, since it has 2 vertices here and 1 ideal vertex here.
Which means the interior of the domain is
Actually, just realize it. I'm not sure how to hide this sign here, since we don't see. No one knows. Okay, so I don't know. So here is -1 divided by z plus 1.
The region under setting and see those. Here appear a fundamental region of this set, generation of integrations and translations. This fundamental region is a polygon. That means inside adjacent segments, so we call it fundamental. Natural question is the following. Here, in line with the is it fundamental function triangle? Let's start with the answer.
Actually, she's saying that if you take such discrete function groups, then you just achieve. Then there will be just some polygon which is translatable by this group and at each point, and for n-dimensional space, this is usually a polytope polyhedron.
We don't need a number of sides that is scalable. We associate its size with rows. Once they read side there, corresponding to an evolution sigma is the set of sides. We also want to comment that and show it by choosing the starting point for each side. Then we consider the following process. We start from one side and its starting point and look to the other side. Then we explore the side which is adjacent to the side.
So those are sides that are reflected to each other.
We point of our side and so we have a cycle that we call elliptic cycle. Let's take an example how hyperbolic polygon can be formed. We can limit the number of sides by splitting one side inside the other. Now, since cases go are transitive projections, it contains some circular transformation. Here is the elliptic cycle. We can also see by getting images of field through the dimensions. Besides known as the error cycle, is here the rotation of the first one is an error line. If we do it twice, we come back to the original side. In fact, we see that each angle of the elliptic cycle from vertex at type 2 value of Q, the copies of the vertices at least a small angle of the vertex. Let's now use an unequal V with 2 sides of the same size. Let's first size of the cycle representations in this as well. Let's suppose that the rotation coming from the elliptic cycle has an angle which is version to bottom to top, and that this polygon is complete. Then, ensure that the group down is solution and P is fundamental. Here is an energy group. We construct an network with generators corresponding to our cyber transformation segments, adding for relations, the relations induced by our cyber and energy centers. Then we construct. Okay,
this is just some proof. So he just using some generator and generators of our discrete subgroup, and he is just forming some sides of this polygon with these generators and relations between these generators. So let's move on.
So once again, what's the statement of the theorem?
So your plane, so the statement is that your plane is divided by equal polygons or such polygonal domains, like maybe some vertices will be ideal, and then just you and these polygons just will be copied by elements of your function group to each other. And for a non-trivial element, it will just copy one such polygon to the other polygon.
So the such tessellations exist?
Yeah. For any discrete subgroup.
For any discrete subgroup,
Yeah.
there is a tessellation which has some fundamental domain, which is a polygon.
Yeah.
Right?
Yeah. As far as I know.
So for all function groups,
Actually,
for all discrete subgroups of the group of Möbius transformation.
well, yeah. So if you at least if you have at least if it is finitely generated, and I didn't sort through if discrete subgroup is always finitely generated. Probably yes. Okay. So let's move on. So actually, there was an article for generating such for embedding trees into hyperbolic plane or hyperbolic spaces. Yeah.
This is the same as only as in
Нет, это не вполне разрывное. Что? Oh, okay. Let me what is discrete subgroup? Discrete subgroup is okay. Let me show you then what discrete subgroup is. Yeah, I just thought this is just very initial, but okay, yeah. Thank you for your question. You just show my mistake. So okay, yeah. Well, for example, here or actually I forgot. Yeah. So this was in another slide, but yeah. So this will also work, but let me show it on this example of Möbius transformations. Yeah, here. So you have, for example, here you have A, B, C, and D are just continuous sets of parameters, right? So this forms variety or manifold. It depends, yeah. What? Okay. You can call it how do you want to, and this is just this is called Lie group, or probably more generally continuous group. So you can consider discrete subset in this group, which is also a group under these compositions. For example, Alexei, for example, take A, B, C, D integer numbers. Yeah, A, B, C, D integer numbers, then this just form a subgroup, discrete subgroup, like this. Yeah?
Okay. Now it's clear.
Or probably you can take not integers but some other set of what? Gaussian numbers are just when you so we have usually we have here so for upper half plane we have A, B, C, and D real, not complex but real. So Gaussian numbers won't work here. But for example, even natural numbers is the same. Just don't remember any good example right now. Okay, this is not topic which I worked through recently, so I don't remember for now. But there are lots of examples. And yeah, so let's continue for embedding trees. So naturally, we want to embed some graphs in your in some spaces. How to what for actually? Why naturally? Since you actually your graph can be huge, and you maybe might need to check the adjacency of two vertices by checking the distance between embedded vertices. This is much more computationally efficient to do than to just store all the list of all edges here. Yeah, so the list of all edges might be huge, and you can just check the distance between 2 points if it can be easily computed. So, okay, I just going to explain to you, but you are not listening, and then you are asking all of a sudden. Okay. Now what we do here, we are just trying to embed any tree in hyperbolic space. Maybe not actually. Let's improve my presentation. So what is it doing actually? And also I see. Okay. So this is just generating a tiling from function group, and this is just deriving the tree from it. And I want to explain it to you in details, so look in the article how to do this, but let's solve a simple exercise for constructing. So let's solve a simple exercise, maybe not so simple, but okay, we will know what is happening here in this algorithm. So okay, first of all, let us let us compute some function group for this tessellation of ideal triangles, and yeah, so let's solve it right now. So what do we do here? We just need to construct such a group of transformations that will send our ideal triangles to each other. This is firstly. The second thing to do is just to do what? So you have, for example, a point in your triangle, yeah? So there will be lots of reflections. So it is reflected somewhere here in this triangle, somewhere here, and somewhere here, right? For just neighboring triangles. So then it is mirroring into this triangle, into this triangle, into this triangle, this triangle, this triangle, yeah? So you are just forming a binary tree here, yeah? So this is the meaning of this exercise. What?
Do we know the group after that?
No, we just want to construct it from this painting. Yeah.
So the exercise is to complete.
What?
The exercise is to complete the group, right?
Yeah. So then we just simply generate a tree, like taking a point and then reflecting it with your group action.
So there's no reward given.
Well, we will know everything, but for now we just know that these triangles are reflected to each other. Yeah.
Okay, but can you give me the idea how do we extract some information from that?
Very simple, actually, to extract. So, I told you that firstly, you just can put each three of your vertices on plane in each other three, even for ideal vertices. Then you will just put them into other three ideal vertices. And then what? Then we just consider this as a very symmetrical painting. So those are, so let us denote this, okay, maybe thinner. Okay, this is a 0 angle, this is a 120 degree angle, this is a 240 degree, yeah? Then what, actually? Then naturally we just, where this should be? This should be on 300 degrees. This should be on 60 degrees. This should be on 108 degrees. And actually all the others are just division by 2. So this is in the middle, 270 degrees. So here 90 degrees and so on. And then we can compute coordinates for this. So those are just degrees. So let's think of 0 point here. So this point here then is 1. This unit disk. This point here is I, imaginary unit. This is minus I, and this is minus 1. So what are these points? So these points are, this is a rotated imaginary unit over the angle of 120 degrees counterclockwise. So what is the transformation here? So this is just I multiplied by cosine of 120 degrees plus I multiplied by sine of 120 degrees. Sorry, not plus, minus. Of course, minus. Since we are rotating counterclockwise. Do you understand what I just did? So
I mean, the only thing I don't understand is that where the magic starts.
Okay. We will see the matrices. For now, we just need to compute some transformations for like fractional linear transformations. Matrices will start shortly.
I mean, where the magic starts, not matrices.
What?
Where do I see the group here?
Okay. You will just derive it soon. Don't haste. Okay, so this is symmetric. I multiplied cosine of 112 plus I multiplied sine 112. Actually, if you have any questions, how do I compute in it, just ask. And this. Слушай, ну не дави уже, а. Неоткуда знать, кто что знает вообще. Ну, елы-палы, задолбал уже. Я просто переспрашиваю, и как бы кто-то может меня перебить и что-то спросить. Задолбал уже. Душнишь вообще. Сейчас проветривать начну. So here we have rotation of 60 degrees, yeah. And yeah, here. So actually, how to, so what to do actually? How to compute any motion. So let us do the following. So let us take this triangle here and see how it can be mirrored to this triangle here. So, why is this? Well, since you can translate it here, then it is symmetrical relation, yeah, mirror symmetry along this line, not alone, but across this line. So, and then you just put, for example, a mirror symmetry across this line and this. Actually, you will just need to take symmetries across these three sides, and then take this as generators for your group. And this is the whole idea for this exercise.
Reflecting a triangle over one of the sides, right?
Yeah. So
these sides are parameterized by the points of the idea. That's why we have just marked.
Yeah, something like this. So you just need to reflect this point to this point, and these 2 points should stay here. Okay. So what I forgot to do is just to say to you that there are just other type of motions, which is function of, which is a fractional linear function of z conjugate. What? Actually, this is for well, if you don't put the bar here, then your fractional linear transformations will be preserving orientation always. This is a notion from complex analysis. All homomorphic functions are just keeping the rotation. So if you take the bar, yeah, you can also add symmetries, mirror symmetries. So, well, this is the idea. Okay, so let's compute A, B, C, and D here for this. So you just, I is the image of I. So here I write something, equation like this. Yeah. This thing, actually I didn't compute it, but let me just denote it as point. Tell me the letter. Tell me the letter. Okay, this will be K. So K is A, K bar plus B divided by CK bar plus D, right? And so tell me 2 letters. Give me 2 letters. L and M. Okay. So we have something like L. Oh no, not L, but L2. Yeah. So M is a reflection of L. So here we have M equals to A L bar plus B divided by C L bar plus D, and probably also for computing all four parameters A, B, C, and D, but probably we already know what it will be. Well, okay, let's just put it here. So L is AM bar plus B divided by CM bar plus B. So we will just now know what A, B, C, and D are by taking linear equations. So by solving system of linear equations. So we have I multiplied by CI bar plus D equals to, oh, sorry, by I multiplied by this equals to AI bar plus B, then K multiplied by C K plus D equals to A K bar plus B M multiplied by CL bar plus D equals to AL bar plus B. And well, we may write it, but this is just will be equivalent. So there is enough information for coefficients already. So this equals to AM bar plus B. So this is the first equation. Second, third, this is here, and fourth. Then these equations are linear on A, B, C, and D. And then you just compute A, B, C, and D. So you just take your, so you just compute your generator, which is in your point. So probably you already know what to do next. So just solve this system of equations. Actually, we know the values of I, K, M, L, and L, and then this will give you one of the generators. Then the other one will be given by computing the other reflection. Actually, the other reflection can be computed as rotation over angle of 120 degrees for this reflection. So just multiply by corresponding complex number, and this. So just to compute this, you just need to compute one generator.
So this equation could have two generators.
What? Yeah, actually, there will be enough for two generators here, since the third will be expressible by two others. Yeah, so.
I mean, usually when we do such planes, we have to prove that we can indeed generate some group with these two, and it will be the same group as the one we wanted.
Mm-hmm. Yeah. So actually, my tessellation of by ideal triangles were given to us, yeah, and from above, I don't know from where, so I just put it here, and we computed something, yeah. So sometimes you just construct it from idea. So and this was actually the idea from the article I mentioned. And now, if you don't have any other questions, let's have a break for 5 minutes. Actually, you can think about what I just said and then ask after the break.
Ну, просто вот мы нашли, допустим, два генератора. Но если уж хочется говорить в терминах генераторов, то нужно, конечно, про соотношение. Иначе мы вдруг не знаем, может быть, не свободно.
Ну, конечно, мы не знаем, как группу с точностью до изоморфизма,
Хотя,
если
кстати,
мы
это
возьмем
дерево,
соотношение.
скорее всего, это есть.
Ну, тут соотношений нет,
Да,
да.
да, это свободно.
Вот, а если бы там было что-то другое, то соотношения бы, конечно, были.
Просто мы пока никак это
Ладно,
не доказали,
ну да.
потому что нам не нужно действительно. Ну, как бы люди, которые что-то про это видели, допустим, поймут, да, что раз это дерево, то, наверное,
Ну, в общем,
соотношений
тут
нет.
вот эта вот теорема нужна только для деревьев. Вот. А если у тебя нет...
Какая теорема? Пуанкаре, то, что назвал?
Ну, вот, в общем, вот это, да, вот эта теорема.
Ну, где видос...
Нам
с
сейчас
полетами
она нужна была
есть.
только для деревьев.
Мгм.
Вот.
Просто, ну да, клево.
Вот.
Наверное, это просто важно.
А так
сказать.
она, конечно, там еще много где.
А то, если в графе петли, то все.
Ну, если в графе петель, на самом деле, конечно, там, да.
Там целая наука про связи. Репрезентация графа.
Кто хотел.
Можно теорему еще все-таки?
Да. Ты сказал 14 предложений, когда я спросил,
Да.
что за теорема,
Я
и
не
я
знаю.
забыл.
Я понял, что что-то про tessellations, но в чем сама теорема, я не понял.
Я понял в определенной степени, так что я не смогу, 5 предложений представить сейчас. Но это
Ну,
не хорошо.
в целом, сейчас.
Ну, то есть, да. Мы понимаем, что курс позиционируется как обзорный такой, да, шапочный проходим, но все равно хочется извлекать из этого какую-то информацию.
Ладно, я скажу, теорему полезно. Доказывать я не хочу, просто там расскажите, что это.
Это не совсем оно.
Там просто 18. Да, было 18. Это не 18. Ну,
Он теперь только на следующем году.
можно попробовать сейчас. Вот я говорю только 17. Сейчас 17 начали.
Нет, нас не повезло кого-то там застать. Кто-то может там до 6.
Вот.
Можно сходить. Если там еще все будет.
Но, короче, Алексей, тут минимальная формулировка не в 5 предложений.
Понял.
Вот.
Она такая.
Ну, я повторю во время.
Это она? А, нет,
Ну да, это
определение,
определение, а потом, значит, теоремка, сейчас, да, вот. Теоремка сама вот,
А, ну
тут
да,
говорится
да.
про фундаментальный полигон.
Ты ведь еще, чтобы ответить на мой вопрос, должен был определить фундаментальную область. то есть
Да.
понятно, что так. Так, Пуанкаре полигон. Discontinuous. Ну, это тоже что вполне разумно?
Ну, судя по названию, очень так.
Ну, действие неразрывное, действие как раз, ну, я не знаю, что значит разрывное, как бы, она действует непрерывными преобразованиями, движениями.
Нет, это другое. Вполне разрывное действие – это свойство, когда она ее орбиты окрестности, которые имеют не пересекающиеся действия. Вот. То есть, когда она куски какие-то не примешивает.
Угу. Ну, да, понятно, да, эта штука действительно так не перемешивает.
Да. Вот.
Ну, да, как раз циклы и дают соотношение.
Благо, у меня был курсик однажды, который обсуждал. Короче, скрипный формулы
Ну, это вы, да, это вы новички. Вот вы ходили бы к специалистам по теории групп и взяли бы там 5 спецкурсиков. Ну, делал. Ну, я как бы вполне себе статьи писал.
За 4 года сложно даже идти по какому-то просветиться, это реально интересно будет.
Ну, я там не то чтобы какие-то великие вещи делал.
Но все равно, как бы, определенный интерес.
Ну да. Сейчас, минута осталась. Минута осталась.
А может, чуть-чуть подольше?
Так, сейчас Все, сейчас накажу. Okay, let's continue. So I was asked what is one Korea mental polygon theorem is about. Actually, it is formulated very nicely. So there is a notion of fundamental polygon. Actually, you can see the link for the article here. And the formulation is for, well, you can think as a formulation for several pages. This was just simple explanation, geometrical. And yeah, so we just form such a polygon of this form for our group. Okay, so actually, yeah, we didn't compute it, our group for this exercise completely, but I just mentioned to you the idea what to do next. Probably you can ask me something about what to do next. So that's some basic idea behind applications of hyperbolic geometry in information theory. So the next application is about entropy in information, in informational geometry. So what is entropy in the information? Actually, well, there is a notion of informational entropy, which is this can be defined for probability distribution as this thing, this expression, as for elements of your probability space, you just take sum of the probabilities multiplied by logarithm. So the probabilities is sign minus, and then and why it is useful? This is not a course on information theory, so I will just briefly mention. So, for example, if we're computing some letter statistics in text, so we just have by Stirling formula that the number of such texts is computed by these formulas, and by Stirling formula it is asymptotically equivalent to this thing, and this is just 2 power n multiplied by entropy. So entropy is just some asymptotic thing, and this is just an asymptotic bound for some statistical situations. Okay. So actually, in mathematical psychology, we know something like a Weber-Fechner law or psychophysical law, reaction is always proportional to logarithm of a signal incoming to us. Our reaction is logarithmical. So, and well, this is maybe an approximate law, but it has some meaning as we just don't look at absolute changes of a process, but for relative changes of a process. And so we can think as this law is actually implies in construction. This model of psychics is actually implies in some models of neural networks. So this is why lots of exponents are here. This is a relation between neurons, and we can think about entropy as a mathematical expectation of logarithm of probability, and this can be considered as an expected surprisedness for our process. Yeah. Okay. So let's consider what is Kullback divergence between distributions. So
the Kullback divergence is a distance measure between distributions which is widely used in information theory and particularly for machine learning. The equations come in two forms, one for discrete probability distributions and one for continuous distributions. On the surface, however, it's not exactly clear why the Kullback divergence is so useful, but in the Powell summation or integral measures the distance between distributions in any group. To explain why the Kullback divergence is a very natural idea, let's back up and consider what it is we're trying to achieve. What we're trying to do is measure the distance between probability distributions. Let's first give an example of probability distribution. Let's imagine that we have a fair point which is equally likely to be on x or tails. This means that the probability of the x is 0.5. The probability of tails is also 0.5. Let's imagine that we also have a bias point with the probability of heads instead of p, and the probability of tails at q. Do you say anything about how similar distributions are to each other? There isn't a trivial answer to this question. We might be able to make general statements about 0.55 closer. For example, if p is 0.55, then point 2 will clearly be much closer to the fair point than if p was 0.95. Why? Well, the results we see with 0.55 will be twice as much as the fair point, and it would be very easy to compute them. However, if p was 0.95, then differentiating between the 2 points would be quite simple and could be done in really few functions. Determining the difference between two extreme examples of identity. Temperature equal quantitative statements about how heavy they are, is it possible to affect boundary of distance? Previously, we reasoned that a natural way to think about distance between distributions was how easy it was to compute them. The basic way to measure this might be by seeing if distributions assign similar probabilities to the same sequences. As if they assign similar probabilities to the sequences, it implies that distributions are different. Let's think of some algorithm. First, we generate observations using point 1. We then calculate the probability of point 2 generated observations. After that, we can compare this probability to the probability of distributed point generated results. If the output probability is similar, then the point might be similar. But if the likelihood is significantly smaller than the second point, then the points might be very different. Now we quickly calculate what can be this ratio here, which compares the likelihood of observations to each point. Let's go over an example of the closed method. Assume that we have a point of probability equal to x, the p equals to x. We then put the point n times the point observations. Remember about the probability of point 1 generated in the sequence. Where this probability now is quite simple. Whenever we see x, we just multiply by point 1. Whenever we see tails, we multiply by point 2. Let's now introduce point 2, which has probabilities q1, q2 instead. Where we have the probability of point 2 generated in data, then I estimate, we just multiply by q1 for each x and q2 for each tail. These two expressions can be simplified by realizing that the product of the probability
probability of each outcome raised to the power of a number of occurrences. For the first one, this is P1 to the power of number of heads multiplied by P2 to the power of number of tails. We then multiply the ratio of probabilities. We simply apply the first likelihood and the second one. Although these calculations based on unrelated to the kill divergence, believe it or not, one of them will kill divergence measures the exact same thing. To see how, let's normalize the sample size by raising to the power of one number of samples. Then take the log of this expression. We'll then turn on the log rule multiplier to break down exponents. Turn multiplications and divisions into additions and subtractions. Again, drop down the powers, which gets us to this stage. Note that if observations are shared by 21.
So this is why there you can see the relation with entropy.
That number of observations goes to infinity, we expect a proportion of x to 10 to P1 and a proportion of shells to 10 to P2. This allows us to say that in the limit, an interval is P1 and density over n is P2. After some final logarithmic elimination, we then arrive at the final expression. Remember what this expression represents. Normalize log probability and true likelihood divided by the likelihood of the second distribution. All we did was simplify this initial expression for the 20 sample, the basic log rule, and we got this equation. If we look at the discrete tail divergence equation again, we notice that the two equations are equivalent. Furthermore, any circle with full string there are really two classes. In fact, tail divergence is a general form of the normalized log ratio when there are multiple classes. This then gives us a situation for what the tail divergence is. Natural estimate of distance between probability distributions, motivated by looking at how likely the second distribution will be able to generate samples from the first distribution. Since a lot of deep learning is all about following true underlying distributions, the tail divergence becomes a very useful measure. In fact, the cross-entropy loss is equivalent to the KL loss, so by minimizing the cross-entropy, we're minimizing the distance between distributions. That's everything for today's video. Cool.
Okay. So this was a notion of Cayley divergence, which is looking very similar to Hilbert-Cayley divergence. Actually, I don't have enough time for explaining where this idea comes from, why they are relating to each other. So, okay, actually.
Is there any connection with the type of cryptocurrency?
Yeah. They will be soon. Actually, this is the amazing thing. Actually, okay. So first, let me mention about entropy that several notions about entropy. So my favorite lectures on statistics, which can be found in the web, actually they're in Russian. From Vladimir Spokойny, that every statistical method is reducible to minimizing Cayley divergence. So this is why this thing is very important in machine learning. But sometimes you just computing of the logarithm is just taking too long, and people use other things. Okay, so historically it appeared as some physical quantity of a situation. So if we, with increasing entropy, material properties will change. So increasing, this means that you have a mixing of two materials, and then so physical properties are changing, and it is hard to reduce this entropy since you cannot, since it is more harder to extract one body from another when they are already mixed, or for example, two heaps of grain. And yeah, probably, well, this was the idea for another exercise, and also basic distribution, more probably you will have higher entropy of states than not, for example, for binomial distribution. And okay, maybe, I don't know, I'm not sure, maybe we can skip it, about some applications of conditional entropy. So this is a video that the entropy, so Kalber-Kleber divergence is conditional entropy for some distributions, and actually it is so it is how easy it is to predict something from given data. This is the main idea that was mentioned here. Okay, and let me also introduce Fisher information of distribution. So this is just second derivative of entropy over some parameter theta. Yeah. So this is sufficient information. And actually, so this probably you heard about it in your statistics courses, statistics classes, but also it is usable in information geometry. And this is how it relates to hyperbolic geometry. Actually, if you want to study some information geometry, which is actually a very beautiful topic, and actually, it is for some people it is easier to think about statistics in geometrical terms than in purely algebraical. Okay, so let me introduce you a video of hyperbolic geometry of information.
Information geometry is a way to associate the differential geometric structure to a parameterized family of probability distributions. As suggested by the name, this notion of geometry has roots in information and yields surprising insights into many well-known statistical distributions. In this video, I'll discuss some examples of parameterized families whose induced geometry is hyperbolic. This is based on the talk I gave for a probability workshop at the 2022 annual meeting of the Statistical Society of Canada. Since the first talk in the session was an introduction to information geometry, I assume that the audience was familiar with the basics of the topic, as well as being statisticians. For more background, I'll list the links in the description.
So actually, this is some formulas from statistical classes, usual formulas. And actually, you can think about Fisher information as Hessian of some matrix, since you can take several parameters theta. So your parameter theta may be two-dimensional.
This covers some fundamentals of information geometry. Most of what I'll talk about are classic results of information geometry, and I'll link to some of the original papers in the description. For a still reference, everything is contained in the paper, a hollow statistical universe, which is joint work between two. The main focus of that paper is a bit different from this video, and really uses the geometry of exponential families in their inherent problem. As I mentioned in the introduction, information geometry is a way to study the geometry of parameterized families of probability distributions. In other words, if we have a parameterized family f of x given data, where x is a point in the sample space and data is our parameter, there is an associated parameter space m sub data, which is known as the statistical mean. Information geometry allows us to determine the distance between the probability distributions in this parameterized family.
So here we just take all the set of all parameters theta.
We can also calculate other geometric information, such as angles, volumes, curvature, etc., and this will tell us information about our parameterized family. When I first learned this, one question I had is whether it is possible to somehow go backwards and study the distributions in terms of the geometry of the parameter space. In other words, the distributions determine the geometry of the parameter space. Can we go backwards and use the geometry of the parameter space to determine the distributions? After a bit of thought, the answer turns out to be no. For instance, there's no geometric way to distinguish between the parameter space of univariate normal distributions and univariate normal distributions. Because the one partition functions are there, even though their natural parameters and base measures are different. And just using distances, there's no way to distinguish between any two location scale families, since the Fisher-Brown measure will always induce the same geometry. However, it can be possible to tell them apart if you use a higher order dualistic structure. But these counterexamples are a bit unsatisfying. One normal and normal distributions are closely related, so it might not be too surprising that they have identical geometries. And location scale families are very similar to each other, so it's not too surprising that we need to consider more subtle geometric invariants in order to distinguish between them. But the answer still turns out to be no, even if we...
So Fisher-Rao metric is just a metric similar to Kolberg-Leibler divergence in this with derivation over parameter theta. Okay, let's move on.
Throw away these kind of silly counterexamples. And there's two ways to do this talk. The first way would be what I call an application start, where I write down the associated system of PDEs and discuss characteristics, integral systems, etc. But I think that's pretty unlikely to be very informative. Instead, I'm going to take the opposite approach, where I show some important families of distributions which all turn out to have the same geometry, at least one. In this talk, all the examples will be exponential families with two parameters. And there's a reason for that. It can be difficult to determine whether two abstract spaces have the same geometry, because the statistical manifold is going to be some abstract Riemann pair. But there's a relatively simple way to tell that two surfaces have the same geometry, which is to compute the scalar curvature. When the scalar curvature is the same, the surfaces will be the same, at least in a small manner. So they'll locally look the same, but if you zoom out far enough, you might be able to tell. Okay, let's start with the most basic example. Since this is an audience of statisticians, I'm not going to give a background on the normal distribution. Instead, let me use this example to discuss the Fisher metric, which is one of the central objects in information geometry. The Fisher metric is defined for any parameterized families, and it's given.
So this a metric tensor for your manifold of parameters.
By this expression, where we take the derivatives with respect to the parameter.
We already saw this J case, yeah?
And then integrate over the sample space. For reasonable parameterized families, the quantity G will be a constant definite matrix, which depends smoothly on the parameters. In other words, it is a Riemannian metric. In differential geometry, a Riemannian metric can be used to compute distances, angle,
very funny Romanian metric.
volumes, curvature, etc. The details of how we do this are not important for the talk, but intuitively, the Riemannian metric determines the shape of a space. Now, if we do this calculation for the space of normal distributions, so we take this PDF and we put it into that integral.
So he is just computing these coefficients.
After an exercise in the kernels, we find the following formula. For course in non-Euclidean geometry, this expression might be familiar. It's the Poincare half-plane model for hyperbolic space. Ignoring that factor too, which maybe you
So you can see that sigma is greater than 0, and we just saw this metric already.
made by rescaling the areas. Intuitively, changing the mean and the variance affect the distribution much more drastically when the variance is small. And this phenomenon induces the normal family with hyperbolic geometry. There's so much more that can be said about normal distributions, and their geometry has connections to analytic number theory and even the research flow. All of this can be found in the paper I mentioned at the beginning. In any case, the normal family has hyperbolic geometry. Let's find some other exponential terms with hyperbolic geometry. The narrative multinomial distribution arises from taking independent draws from a multinomial distribution where one of the events is considered a failure event. For instance, if I roll a dice repeatedly until a 1 comes up, the number of rolls of 2 through 6 before the first one falls in negative multinomial, which in this case is the negative sextant. This gives a discrete distribution which has the following probability estimate. We can slightly modify this schema to allow for some fixed number of failures. For simplicity, let's just consider one failure. Here, there are n minus 1 parameters, which correspond to the probabilities of the success events. To simplify, but not oversimplify the geometry, let us specialize the negative trinomial distribution, where there are 2 success events and 1 failure. This gives a 2-dimensional parameterized frame. In order to understand the geometry of this family, it's helpful to reparameterize the distribution. From a geometric perspective, reparameterizations correspond to changing the coordinates of the statistical manifold, which doesn't affect the geometry. It's possible to rewrite this as an exponential family, but for this lecture, we'll actually take the square roots of the success probabilities. When we do that, we can calculate the Fisher metric the same way we did for the normal family, and doing so, we get the following. Again, this is the metric which you might be familiar with if you study non-Euclidean geometry. It's the Klein disk model for hyperbolic space. Intuitively,
Actually, we already seen something like this. This is 1 minus norm of x squared, yeah?
changing the success probabilities P1 and P2 affects the distribution drastically when the probability of failure is very small, because there will be many more draws before you see a failure. On the other hand, when the failure probability is large, changing the success probabilities has comparatively little effect. And this effect induces the parameter space with hyperbolic geometry. There's one more thing to note here, which is, unlike with the normal family, we do not recover the entire hyperbolic line. Instead, we need to restrict ourselves to the set where S1 and S2 are positive, which leaves a quarter of hyperbolic space. The boundary corresponds to the set where the failure probability is 1. Okay, there's a minor diversion that I have to make here because it's too interesting to go unmentioned. As I mentioned a few minutes ago, there are mathematical reasons why we expect to find many exponential families whose Fisher metric is hyperbolic. And so these 2 examples shouldn't be too terribly surprising. However, there's another and much more subtle connection between these families. For any exponential family, it's possible to build a pair of Taylor manifolds on the tangent bundle of the parameter space. This duality is closely related to a concept known as mirror symmetry in algebraic geometry, and this notion of statistical mirror symmetry is actually the main focus of our work. These killer manifolds detect much more subtle information compared to the Fisher-metric level. However, quite surprisingly, the dual killer manifold for the normal family and the primal killer manifold for the negative trinomial family has the same geometry, least score. In other words, even though these distributions are completely unrelated, these two spaces end up being locally indistinguishable. However, their mirror images are completely different. Always for me, this fact was completely unexpected and something that came as a bit of a surprise. Okay, let's see one more example of a hyperbolic statistical map. The inverse Gaussian is another example of an exponential family. As suggested by the name, there is a connection to Gaussian distributions, but it's a bit complicated. In essence, the idea is that if one starts with boundary motion with positive variables, the amount of time it takes for the process to reach some positive value alpha is distributed according to an inverse Gaussian distribution. After dimension reduction, there are two parameters, and we can write out the distribution explicitly. What makes this an inverse Gaussian is that for positive time, Brownian motion will be distributed according to a Gaussian distribution. In other words, a Gaussian distribution describes Brownian motion's level at a fixed time, whereas an inverse Gaussian distribution describes the distribution for the time that Brownian motion takes.
Actually, it's also distribution that naturally arises in Bayesian statistics for Gaussian distribution. Okay.
To reach the fixed positive level once you add some positive. We can use the same process as before to understand the geometry of the parameter space of inverse Gaussian distributions with parameters mu and lambda. Computing the Fisher metric, we find the following. The scalar curvature of this metric, so we're just going to compute that out, satisfies scalar is identically equal to -1, which means that this is also a hyperbolic metric. Albeit its geometry is exactly half of that of the other examples, the scalar curvature was negative. The change of coordinates to relate this geometry to the halfway model isn't immediately obvious, but was found by Ola and Blair. Doing so, we can see that the parameter space is geometrically equivalent to half of the halfway. In other words, is a quarter. And so again, like with the negative trinomial distribution, there's a boundary. We don't get the entire hyperbolic.
Okay. So now he continues to applications for Brownian motion, but actually for, I don't know, maybe brain sciences or something like this. This is just, these distributions are probably, seemingly very important, since lots of things are normal and we are learning from our successes and failures. So this just relates to some hyperbolic geometry, actually. So there might be some underlying geometry behind, and we will talk about it later today.
When we conclude this video with a probabilistic result, which is straightforward to show geometrically, but might be difficult to draw outcomes. The symmetry group of the hyperbolic pathway is well known and corresponds to Mobius transformations which satisfy AD minus BC is equal. However, most of these transformations will not fix the line x equals 0, which we need in order to obtain the symmetry of the inverse Gaussian dynamic. However, if we scale the half-line, this fixes the line and preserves the hyperbolic metric. The fact that scaling generates a symmetry has a natural interpretation as it corresponds to scaling the direct min and the level alpha for the original stochastic process. However, until you do this computation, it's not so straightforward to show that the scaling preserves the geometry. It should be noted that there are other symmetries which fix the line x equals 0, which correspond to an invergence or unsurface centered at the origin. I don't have a good statistical explanation for what these transformations correspond to, so I'd be very happy to hear if someone else can explain.
So this is some slight application for some physical problem, and this is just a new way of thinking of it for him. So this is just an application, some interesting for mathematicians.
Thanks for watching, and please leave a comment if you have any questions.
Okay. Okay, so that's it. So yeah. Now I continue to. Well, actually, there were a whole bunch of such articles. Like here is an article from Nature Journal. So there. So let me show you. Let me show you. So let me show you the title. So brain embeds spatial information in somewhat like a hyperbolic geometry, and how it was found out. Actually, they just did the following things. Well, roughly speaking, I won't go into details. Try to read this article for yourself if you are interested. But the method behind this, in context of hyperbolic geometry, is the following. So they just took some. So they just took some geometry. How to say this? So they computed some informational distances between neurons, roughly speaking, very roughly speaking, and then they just compared it with the distance matrices with different geometries. So probably I should switch the screen and try to explain it more thoroughly. Okay. So if you have so you take some matrix of distances. This so Dij is a distance between I and j neurons. I think j's like this, and then you are trying to embed it in some spaces for nearly preserving this matrix, or at least nearly preserving the distribution that was sampled statistically this way, and how to compare with some geometry actually. So we just use formula for, let me find it actually. Yeah, here. So I will just copy. So you just do this thing. So for example, you are sampling on a circle endpoints, and then you just try to know which what is the distribution of distances between these points. So they are all distant from some central point for R. So this is a local comparison of geometry. And I will talk about why I am considering local comparison. So you just so there are lots of points in higher dimensions. You should sample on spheres, and then you just consider the distance matrix behind them, and for 2 points, you just try to consider what is the distance between these points. So this will give you a distribution of your of distances on 2 points on the circle, or related, for example, use the numbers as n, for example. Yeah. So the easiest way to do the easiest way to compute this is to compare the formula for distance xy for the triangle XY, and this is doable by this. So I will just give you a rough idea. But so actually in Euclidean geometry you have something like this. This is in Euclidean geometry. Yeah, cosine law, and for hyperbolic geometry you will have something like this. So hyperbolic cosine of xy may be divided by something, so roughly speaking. So cosine of x or x, cosine of y minus here, sine, hyperbolic sine of x, hyperbolic or x, sorry, hyperbolic sine of y multiplied by usual cosine of alpha. Okay. So let me write it more clear, like this. So I'm just repeating this formula for this triangle. Okay, so OX cosine of OY minus hyperbolic sine of OX, hyperbolic sine of y, and then multiplied by usual cosine of alpha. So and then to compute xy, then you take like hyperbolic cosine of this thing, and then you compute a distribution. Well, that's the idea. Actually, let me actually speak about some general ideas here, since actually we are not expecting here just simple hyperbolic space for any situation, actually, for any research, since actually what can be here. So here we consider an information space as a two-dimensional hyperbolic plane, yeah, and probably we have something like n-dimensional hyperbolic plane. Probably we have just a product of two hyperbolic planes, and here the distance between 2 points, even locally, should be different actually. Probably we have another hyperbolic, hyperbolic-like manifold. Hn1 times Hn2 times etc. times nhk, and probably times Euclidean space RL, and probably times several spheres, for example, yeah, SL1, L1 dimensional, L2 dimensional sphere times Lm dimensional sphere. So in these geometries we can do the same thing, and then to compare our statistical distribution with what is prescribed from here. Yeah. So okay, and now I want to don't have much time for discussion of this, but that's some idea behind. Probably you can ask me some general questions like what is the distance between 2 points in this geometry or something like that. Well, so this is the way how to compute things and compare. So what else to do? Now, actually, about the brain sciences. So one notion that I want to mention is that actually probably we don't have a whole hyperbolic plane or hyperbolic space in our psyche, I don't know, in our mind as a structure, since brain is just finite thing, and you can consider it as a finite computer. So probably this hyperbolic space will be cycled, and this is just a locally hyperbolic space. So let me show you again what I showed you at first lesson actually. So let us move to the part 2 of art. I told you about the idea here is that, yeah, so you can glue some bodies, some manifolds from parts of hyperbolic plane, and then consider it as a local hyperbolic manifold. And then, well, this is what I showed you here while gluing this poly from some surface from this quartic, from this polygon, yeah. And this was actually an example of a hyperbolic manifold. Actually, there are whole books about hyperbolic manifolds and how to construct them. They are all constructible in the same way by using function groups, and yeah. So actually, I am expecting something that something like that. We have here hyperbolic manifold. Well, and talking about the brain sciences, we have well, yeah, is the conclusion, and well, let me say the conclusion after the short break, actually, since it is time for it. Yeah. So 5-minute break, and then continue. Okay. Dear Meatbags, let's continue. So, yeah, that's what I already did. And yeah, actually, there were several other experiments which can be found on YouTube about this topic of brain and hyperbolic geometry. Actually, let me just show you some provocative study. So this is about psychedelic trips and people are talking about that they saw some strange pictures, and these pictures are branching everywhere. So this might be another how to say this, another fact for consideration of hyperbolic geometry here. I am not recommending you to check this by yourself. Okay. And conclusion here is that our brain is adjusted to local multidimensional hyperbolic geometry and is happy with it. And so we embed information in hyperbolic space or probably hyperbolic manifold, and then organize somehow information flow, and this gives us idea for methods for neural networks. Those are called hyperbolic neural networks. I will shortly talk about some formulas from these neural networks in final lesson, but I won't discuss anything like code or what to do here. Just like ask ChatGPT or something, and it will write you some code for it. And sometimes with these commentaries. Okay, so actually, probably you have any questions for now, no? Okay, so no questions for now. Then let's move on to physics. And actually here I want to, well, probably we won't watch all the videos I prepared for you, but at least shortly I need to remind you what is phase space about. Okay. So what phase space is about? So you can so let we have some physical problem with maybe some points, something general physical problem. Then we have coordinates of our points. Let's name them QIs, and also some moments for these points. Let's call them PIs. So, and actually, usually in physical laws, at least no physical laws that I know, we can solve this. Usually, this is somewhat like m1 multiplied mi multiplied vi. Yeah, but in relativistic theory, this is not the case. Actually, well, it's nearly the same thing. So you just consider not impulse. I said generalized moments. Yeah, it's generalized impulses, and actually accelerations here are just the functions of Q and P for the whole system. This is how physical laws are usually written like. Some expressions for this, and physicists here are introducing Hamiltonian function of Q and P. So we have something like, and actually we have something like derivation over time equals to partial derivative of h over y, and velocity over time of coordinate is minus derivative of Hamiltonian relative to over pi. Maybe I'm not correct. Maybe I just misplaced minus sign here. Maybe it is here instead of here, but it doesn't matter for now. So this is so-called Hamiltonian mechanics. So here is Hamiltonian formulation of mechanics, and actually this shows us some duality between coordinates and impulses. So we can consider, for example, for different Hamiltonian function, h tilde of P and Q, yes, h of Q and P. Well, okay, I swapped sign probably, yeah, here.
Yeah, you swapped the sign, you forgot the time derivative for P and Q.
What I forgot? Yeah, P prime. Here is P prime. Yeah, it's prime.
Yeah, then we consider
Okay. Well, I just adopted it. I need to write it here about it. Never mind. So there is some duality of Q and P, and actually this, for example, you are deriving your current position from impulses and probably initial conditions, and this is some statements from Hamiltonian physics, Hamiltonian mechanics, and actually in relativistic physics we have such notions that here velocity is lesser in absolute values than speed of light, as was stated in relativistic, especially relativity theory. So this velocities form a ball of radius c. So actually, usually in classical Newtonian mechanics, we have something like this is just Euclidean space, but of impulses, right? but in relativistic physics, it is just like hyperbolic space of impulses. And yeah, so well, this is roughly a formulation of special relativity theory, very roughly actually. So probably we can watch several videos about it, and here there will be introduced some okay. Okay. So I will answer to this later. And okay, so this is a formulation for phase space. Actually, recommend the channel of the author.
In this video, we'll be talking about Hamiltonian dynamics in phase space. Let's consider Hamiltonian H, which is a function of generalized positions Q and generalized momenta P. These are vectors where Q ranges from Q1 to Qn. This could be a system with n generalized positions or a system with one generalized coordinate in n dimensions. And the corresponding generalized momenta range from P1 through Pn. The space divided by all the generalized positions and all the generalized momenta is called phase space. Hamilton's equations involve all of these positions and momenta forward in time, which means we need two n coupled first-order equations to fully determine the dynamics of a system described by the Hamiltonian H. Hamilton's equations are the rate of change of Qi is equal to dH by dPi, and this is some function we're going to call Fi of the vectors Q and P. We have an equivalent equation, the rate of change of the generalized momenta Pi is equal to minus the derivative of H with respect to Qi. This is equal to some function G of I, which again is a function of the vectors Q and P. This description of the dynamics is in contrast with both the Lagrangian and Newtonian methods, which give us n coupled second-order equations for each system, and these aren't always easy to solve. But let's see what we can do with Hamilton's equations. We can write each of these as vector equations, where the rate of change of the generalized vector Q is given by some vector function f, which is itself a function of the Q's and the P's. And likewise, the generalized momenta evolve according to some vector function G, which is again a function of Q's and P's. In phase space, there's no reason to treat these coordinates differently from one another. So we can combine them into a single vector, let's call it Z, and we're going to get this by stringing together all of the generalized positions and all of the generalized momenta together into one large vector. This vector Z is a point in the phase space of our system. Each point in phase space corresponds to a unique set of initial conditions. That is, each point Z tells us where each particle is located and what their momenta are at any given point in time. The entire dynamics of the system are obtained by evolving this point forward in phase space according to Hamilton's equations. So in phase space, the rate of change of Z is given by some vector function H, which is a function of the Q's and the P's, which is obtained by stringing together all of the Fi's and all of the Gi's, and this gives us the full dynamics of the trajectory in phase space. This type of dynamics is something we've had a lot of experience solving. We studied a bunch of dynamical systems models, including the predator-prey model. Here's an example of the dynamics we saw. The x-axis is the prey population, and the y-axis is the predator population. The blue arrows represent a vector field that describes the dynamics of the system. The x component of the vector field describes the rate of change of the prey population, and the y component of the vector field is the rate of change of the predator population. We analyzed this using the slope field method. Every point in this space represents an initial condition, the number of predators and the number of prey at a given instant in time. And integrating along this vector field, we get the total dynamics of the system. The exact same thing happens when we look at Hamiltonian dynamics in phase space. Here's a plot of phase space where Q is on the x-axis and P is on the y-axis. This can be analyzed exactly the same way we did with the dynamical systems model. We treat the vector field as a velocity in phase space, where the components of the velocity are given by Hamilton's equations. Z dot is equal to dh by dp and minus dh by dq. Any point is at an initial condition, and the streamlines, which are the trajectory of my system, just flow along tangent to the blue vector field. In the rest of the video, we'll explore the consequences of this type of dynamics on phase space. The trajectories we just solved for, the solution to Hamilton's equations, are called orbits in phase space. Starting at a particular set of initial conditions given by a point in phase space, we integrate along the vector field and we get a phase space orbit. One of the most important points we'll make today is that starting with some set of initial conditions, Z naught, the resulting trajectory in phase space is unique. This is a theorem. I'm not going to prove it right now, but we'll need it going forward in order to prove some other results. A consequence of this is that no two trajectories can cross. We'll prove this by contradiction. Imagine that we have two trajectories that do cross at some point Z prime. Then if Z prime were an initial condition, it would have two or more trajectories starting from that point, and this violates uniqueness. This implies that phase space orbits can never cross at any point in time. Imagine we have some point Z naught in phase space, and we're going to evolve our dynamics forward in time to Z naught of t. Let's take a neighborhood of points around Z naught, and we'll call it A. And we're going to flow all of the points in A along in time too. That gives us a neighborhood around Z naught of t, and we'll call it A of t. We'd like to show that any point that starts in A ends up in the area A of t at a later time. For example, this point here starts in A and ends up in A of t. This tells us that neighborhoods in phase space remain connected for all time. That means that instead of looking at individual trajectories, we can simply look at the entire trajectory of A to get the full dynamics of our system. In order to prove that, let's assume that some point B that starts in A doesn't end up in A of t at a later point. Here are regions A and A of t, and the trajectory of some point Z naught. Imagine we have some point B that at time t ends up outside the region A of t. Then the trajectory of B must cross the trajectory of at least one point in A, and this violates uniqueness. Most of what we've looked at so far has been 2D, but this applies to higher dimensions as well. Let's consider a higher dimensional system. A of t is some region in phase space that is bounded by the path gamma. We'd like to know what happens as we flow this forward in time. We're going to move it according to Z dot by some amount delta t. This is going to give us a new region at A of t plus delta t. It's bounded by the curve gamma of t plus delta t. What happens to the region A as it flows along according to Z dot? In particular, does the volume of A change as we evolve it forward in time? To explore this, let's zoom into a little section of the boundary gamma. This vector n is perpendicular to both the curve gamma and to its parent surface A. We'll look at some infinitesimal piece along this curve delta gamma and evolve it forward in time according to V times delta t. To calculate the change in area as we change gamma, let's look at the volume of this infinitesimal area element. The volume of this area element, dA, is equal to the surface normal dotted into the vector V times delta t, which is the projection of the flow direction into the surface normal. That's the bit of the flow that's perpendicular to delta gamma. Then we multiply it by delta gamma to get the total area of this little patch. Now, if we want to look at the change in area of the whole patch, we need to integrate this over the entire half gamma. So the change in area is the integral along gamma of the surface normal dotted into the velocity field times delta t. We can calculate this line integral using the divergence theorem. The divergence theorem states that if we have a surface A with a normal vector n The integral around the boundary of the surface gamma of the normal dotted into some vector field V is equal to the integral over the surface of the divergence of V, where the divergence is equal to dV by dx plus dV by dy plus dV by dz. So in the limit that delta t goes to 0, the rate of change in the area in our region is given by the integral around gamma of n hat dotted into v d gamma, which according to the divergence theorem is equal to the integral across the surface A of the divergence of the dynamics of z dot, and we'll find out in a minute that the divergence of z dot is equal to 0, so the area doesn't change. The statement we just made is actually a theorem by Liouville. The volume of any closed surface in phase space remains constant as that surface moves throughout phase space. It turns out this is a consequence of trajectories never crossing. The divergence of the velocity field, which is the...
Okay. So there will be a theorem. Okay, maybe. So that's why some things like entropy is important and so on in physics.
Given by Hamilton's equations, z dot is equal to 0. We can show this explicitly by taking the divergence of Hamilton's equations, which are z dot equals dh.
Well, okay. This is some explanation of phase space, and yeah, duality of coordinate and impulses. Actually, what I wanted to mention here is that you can consider the present moment as a function of impulses if you can solve the corresponding Hamiltonian equation. So actually, I come up with a joke that when I prepare this lecture, that your present self is a function of your inner impulses, and they live in hyperbolic geometry, and your brain is living in hyperbolic geometry. So you may start your whole new age philosophy from this point, and probably have some usage of it or not. I don't know. For me, it's just very cool mathematics with some applications. Okay. So next, let probably start to talk about relativity theory. So actually, there were two videos about swapping space and time. Probably you would like to see them. If not, if you do, tell me. Well, this is how it will look like. And yeah, so since there are no reaction from you, so then yeah, I just move on. So actually, in relativity theory, actually swapping space and time is usual, since we have something like Lorentz transformations here. So I already told you that we have a whole group of transformations of your hyperboloid, and you can, and since our impulses are living in hyperbolic space, so they are transformed by this Lorentz group. There is a visualization of how this group acts actually. Well, if you would like, I would show you. And if not, I just continue. Okay. So what's next? Actually, Actually, I wanted to talk with you about some formulas from special relativity with comparing to hyperbolic geometry. So actually, you know that velocity is not larger than speed of light, but this holds in every system of coordinates. So when the ray of light is moving, then against him another ray of light is moving. So soon they will meet, but you can guess that usually the addition of the velocities is just give you that they are moving to each other with 2 times speed of light. Yeah, but that's not possible in special relativity theory. So here is velocity addition law from physicist Albert Einstein. So, and you can compare this formula, with addition law of hyperbolic tangencies. And actually, I looked for this formula in several sources and found just something like this. And this means that this velocity of B related to A, actually this should be divided by the speed of light here. So then this is something like hyperbolic tangents. Okay, this book for Soviet schoolboys. And actually, when your velocities are not on the same line, then you just solve hyperbolic triangle. I already showed you what the formulas are for hyperbolic triangle. So you can use this in your practice if you want. And there was a visualization of how lengths. So since velocities are recomputing in special relativity theory, so do lots of other things like masses, lengths in different systems of coordinates. So this nice visualization from this channel. Actually, I also recommend this channel since there are lots of very good stuff, very good visualizations on this channel for example, relativity theory.
Welcome back to Science Quick. Today, what will we see if we approach the speed of light? Let's embark together on a spaceship which accelerates away from Earth, moving faster and faster. What would we see when constantly accelerating? What optical effects will occur? And if we try to exceed light speed by bending space-time like in sci-fi movies, what would we see? Answering these questions will lead us to explore many fascinating phenomena of our universe and immerse ourselves at the heart of special and general relativity. Our spacecraft is initially at rest. Once launched, we begin to accelerate. We imagine that its propulsion system allows us to accelerate constantly as long as we wish. As we gain speed, we move away from Earth. By accelerating more and more, one would think
I see, okay, so, sorry. Probably I just clicked something on my phone. Okay. Which moment did you saw the last? Okay, probably 1 minute ago.
the system allows us to accelerate constantly as long as we wish. As we gain speed, we move away from Earth. By accelerating more and more, one would think that the speed would eventually become unbearable. However, this is not the case. Speed has no effect on our body. When two trains cross, it is impossible to feel whether it is our train or the other which is at rest. Similarly, inside the spaceship, we cannot feel its speed, but only its acceleration, the thrust of the reactors which press us against our seats. If this thrust is reasonable, it will be perfectly bearable all along our journey, even when approaching the speed of light. There is nonetheless a risk associated with very high speeds, a collision. At high velocity, a mere speck of dust would cause colossal damage if it hit us. Fortunately, our ship is equipped with a force field that repels dangerous objects and allows us to roam freely through space. As we accelerate, a first optical effect appears. The stars in front of us, which we get closer to, seem to gradually move away. The sky contracts before us. To understand, think of this common situation. You are in a car driving at high speed, and it starts to rain. The rain falls vertically from top to bottom, but as the car moves forwards, you receive raindrops on the windshield from face on. The rain does not appear to fall from above, but from the front, as if its trajectory were tilted. And the more you accelerate, the more the rain seems to come from face on. In our spaceship, the optical effect is perfectly analogous. The star's light comes from a certain direction, but as we accelerate, the light rays appear to come more and more from the front. Their direction seems different when we are in motion. This is the aberration of light. As light focuses in front of us, its intensity increases, while behind us, the sky seems to widen and becomes darker. The aberration of light results in another strange phenomenon. Let's imagine we are moving through an immense grid representing the fabric of space. Ordinarily, we would see a straight grid made up of straight lines converging in front of us due to perspective. However, by speeding up, the aberration phenomenon distorts the image of the sky around us as the days go by. The grid seems to contract forward, and the straight.
So I just like how he draws these circles here.
Lines bend. If we were to go past an object, it would appear to be slightly angled in our direction. This is called Terrell-Penrose rotation. As we move very quickly, images of objects seem contracted in front of us, and perspective is strongly distorted.
So here he was drawing hyperbolas.
We offer here that the further we look into space, the further we look into the past. Indeed, the light we receive from a distant star must travel billions of kilometers. This journey is not instantaneous, and it takes some time for light to reach us. As a result, we see the star as it was in the past when it emitted this light, perhaps several thousand years ago. Who knows how it might have changed since then? Looking up from our spaceship, the same phenomenon is at work. As we move away from Earth, the planet's light takes longer and longer to reach us. If we could zoom in with a telescope, we would see people on Earth evolving in slow motion. This is the Doppler effect. Each tick of the clocks on Earth takes longer and longer to reach us. We receive light rays in slow motion, and their intensity seems to weaken as the image of the planet shifts towards red color. In front of us, it's the opposite effect. The ship catches up with the light, and the stars seem to get brighter. They shift towards blue color, and their clocks seem to tick faster. With precise enough equipment, we can measure the aberration and Doppler effect since the start of our acceleration in space. However, if we decided to end our journey and return to Earth, these effects would have no impact. They are only optical illusions due to the way we receive light while moving. After several hundred days, however, as the reactors push us ever faster, the ship begins to approach light speed. At such speed, some phenomena will no longer be mere optical illusions. Real physical effects will kick in with irreversible consequences. Special relativity comes into play. A first consequence of relativity is known as time dilation. Our universe is a huge four-dimensional fabric called space-time, made up of 3 dimensions of space and 1 dimension of time. Inside space-time, all bodies trace their trajectory since they all advance towards their future. Before takeoff, our ship was moving in the same way as Earth towards the future. But by picking up speed and zooming away from Earth faster and faster, our trajectory gradually deviated from that of the planet. The axis we call time is no longer aligned with the time axis of people on Earth. If we decided to turn around and come back, our clocks would have measured a different time, and we would have aged less than Earthlings because our trajectories in space-time would have been different. Another key consequence of special relativity is called length contraction. When a body moves at close to light speed, its length gets contracted in the direction of its motion. From the spaceship's perspective, the entire universe is moving backwards. For us, the universe is contracted along our direction of motion. As such, the length of the journey to reach our destination is shorter than expected. We are not talking about optical effects anymore, but of a physical and concrete phenomenon. If we tried to reach a distant star, the journey would generally seem shorter to us. It would take less and less time the faster we move. Thus, contrary to popular misconception, it is in fact possible to travel thousands of light years in just a few seconds. And in the case where we would move almost at light speed, the journey would even seem instantaneous to us. For the people on Earth, however, several thousand years would have passed. Length contraction is a very real phenomenon. However, visually, it would be difficult to see. To understand why, imagine that we cross the orbit of a planet. As it moves very quickly towards us, the planet's length is contracted. But remember, the farther we look into space, the farther we look into the past. And from our perspective, the back of the planet is located further in space than the front of the planet. The image that we receive from the back of the planet has taken longer to reach us, so we see it as it was in the past. Even if it is contracted, the planet does not look like it because we receive the image of its back with a delay. Rather than contracted, it appears to be rotated. This is a phenomenon we have already seen, Taylor-Pepper's rotation. When we move very fast and look to our side, the edges of the objects around us seem shorter in the direction of motion. This can be interpreted either as length contraction or as a rotation, as a change in perspective. For the same reason, a person watching us zoom by would not really see our shape contracted, but rather rotated in itself. Over time, our field of view continues to contract. It intensifies in front of us while going completely black behind us. By accelerating more and more, we would perhaps expect to reach the speed of light at some point. What would we see then? This question might be one of the most fundamental in relativity. The answer is no. Even if the ship accelerates constantly, we will never reach the speed of light. That is because the speed of light is absolute. You may try to catch a light ray, but from your point of view, it will always escape at the same speed, the speed of light. You may accelerate as much as you wish, even if from Earth you would seem to approach the speed of light. From your point of view, you are still motionless, and light escapes inexorably. In short, it is strictly impossible to exceed or even reach the speed of light. At best, our ship will continue to accelerate forever, and our field of vision will continue to shrink ever more, until forming an infinitely bright spot in front of us, surrounded by a completely black sky. Almost at light speed, all multiple effects will become extreme. As we catch up with light waves of...
Again, I just love this forms. This is so hyperbolic.
For us, they all seem to come from the front. Meanwhile, the rays behind us can never reach us. In our frame of reference, the universe would be extremely contracted, like a thin fabric we would cross from side to side in a fraction of a second. For a person on Earth, we'd be moving at the speed of light. But for us, the trick seems instantaneous. We move infinitely fast. To conclude, nothing can ever move faster than light through space. But there might be a way to circumvent this rule. In fact, nothing prohibits space itself from moving faster than light. Indeed, the theory of general relativity teaches us that the fabric of space-time is dynamic. It can bend in multiple ways. We could thus imagine creating a bubble around our spaceship, which we would propel faster than light. This is called a warp drive in reference to science fiction. It would no longer be a matter of zooming a vehicle through space, but of propelling the fabric of space itself. Our ship would remain motionless, surfing on a wave of faster than light space-time. Such a structure may seem absurd, and indeed is currently thought to be impossible to achieve. Producing a warp drive would require bending space-time with huge amounts of negative mass, a form of matter that does not seem to exist in our universe. That said, mathematics still allows us to model and calculate what we would see in such a situation. If we looked from outside, the warp drive would seem to appear out of nowhere. The curvature of space-time deviates the trajectory of light rays, forming a moving lens, which splits into two, one part moving forwards and the other retreating in the opposite direction. Light travels slower than the warp drive itself. When it approaches, light has not yet had the time to reach us. And after it crosses us, we receive both the light which had not yet reached us and the rays which were emitted later. Looking from the inside of the warp drive, we would see the sky contracted in front of us and very bright. Behind us, the universe would look extremely dark, and the whole patch of the sky would simply vanish from our view. The light emitted from there is too slow to catch up with us. A cone of the universe remains permanently invisible.
So, okay. Actually, there is a whole playlist on this channel about general relativity, and just recommending you, if you want to get know some to watch some scientifically correct pictures of it. And I was asked by someone for describing what did he mean in the last few minutes. Is this Alcubierre warp drive? Well, this is how fantastical construction for now. Well, it doesn't contradict for now any physical theory. Just we don't have enough of experiments for what we can do, because well, this is somewhat like a curving, not curving space around us. This is possible in general relativity theory. Well, probably I can show you in the last several minutes how general relativity works, but not with much formulas. Okay. Where it is? Okay, here it is. Okay, so one day, one very crazy physicist introduced me some four-dimensional model for gravitation. So first consider two-dimensional model for gravitation, actually. Let we have a string. And you put several bodies, for example, two bodies on it with masses m and n. So it shortly becomes like this. And what will be the acceleration of the motion towards each other? Actually, acceleration will be proportional to 1 over the distance between them. Okay, this is for one-dimensional universe, actually. So we are living on this string. This is one-dimensional, and here gravitational law is proportional to 1 over r. Let's consider two-dimensional spandex. Here we have two bodies again, and the acceleration is proportional to 1 over r powered by 3/2. And imaginary physical model is when you have four-dimensional space and three-dimensional spandex with gravitation here. What? Yeah, batut. So you can finalize how to continue the sequence. Yeah. So here was 1 over us. Here was 1 r powered by 3/2. So here is usual. Here is the usual gravitational law from Newton, and this is a model, and this is actually the model of gravitation, and this is how heavy bodies are curving space around us. Yeah, so actually you can watch the video on YouTube, for which I already don't have time. Not sure. Okay, probably I should add what functions. Yeah, gravity visualized. So this is a beautiful video for this idea, and so this is a general. So this is very roughly speaking a general relativity theory for mathematicians. And okay. I didn't put it for video translation, so just inserted something somewhere like here. So here how it looks like. And okay, so this video, you can watch it, it's very funny. And so you can do so actually this is what is the relation with hyperbolic geometry? For me, there is not so much relation for them, but actually probably the wave, except for wave equation here, since we have let me show it to you in this way. So for surface of your spandex or your string, you have just a partial differential equation like this, and actually this looks like somewhat like this is called a hyperbolic differential equation. I am not sure what how it is related to hyperbolic geometry itself. However, for example, we can take Fourier transform of it and just get something like this. And this will look like this, a Fourier transform. And so I'm not sure how to make any relation with hyperbolic geometry. Probably it's a future application. I hope that, because it will be very beautiful. Okay, so actually for now let's stop. Let me put on the list who was attending, and actually, do you have any questions for now? What?
Do you get a constraint on Fourier coordinates?
Constraint on Fourier coordinates? What do you mean?
Here's an equation.
Yeah.
This square they call sum square. This is basically a problem. What we call line problem. But like how to interpret it.
So I'm not sure how to interpret it. I just told you some idea.
So it is a weak connection to...
Yeah, very weak connection for now. Okay. Well, I just told you. I don't know anything. I just looked through internet, and this was not okay. So I wrote everyone in chat. Probably not everyone. No, everyone. Okay. So I don't know any connection of this hyperbolic geometry for now for this wave equation. I'm hoping to Maybe I will find out it. Probably you can. I don't know. This is very difficult to imagine, actually, for now. Okay. So, okay. Any other questions for now? No?
Previously, you said that there should be some esoterics on this lecture.
Some esoterics. I already told it to you when I was joking about New Age philosophy. This was actually I wanted to mention that probably our brain for billions of years already adjusted to such things as relativity theory, like probabilities, like standard normal distributions, trinomial distributions, and so on. So actually, they are all essential. They should be all essential. So that's probably one of the best explanation we can have for now. So that's for applications in brain sciences. Any other questions? What's the last? Yeah, one more lesson about advanced computational techniques, like what to do in coordinates in this geometry, like what. Yeah, one more computational lesson.
So, for example, would be compute here.
Yeah, like to work in coordinates, like to derive some formulas for motions, exact formulas, like to introducing new gyrovectors, how to work with them. Yeah.
That's great. So it will be Monday. Right?
Yeah, Monday. Okay, bye. Okay, then I stop recording.